everyone. This lesson will introduce you to the two classes of symmetric cryptography algorithms, block ciphers and stream ciphers. This lesson will cover principles of operation of block ciphers, block modes, input padding, initialization vector, and finally stream ciphers. Block ciphers are indispensable components in many cryptographic schemes. Block ciphers provide confidentiality on their own and are often used as building element in the construction of pseudorandom number generators, hash functions, message authentication codes, authentication protocols, etc. Stream ciphers provide confidentiality of continuous data streams in real time in applications like voice and video calls over the Internet. A block cipher is a pair of mutually inverse algorithms, encryption and decryption, with two inputs, a key and a fixed-size block of data like 64 or 128 bits, and output a block of data of the same size. The encryption transformations are usually built upon efficient operations optimized for hardware computation, such as exclusive OR or bitwise rotation. Encryption is usually carried out in multiple rounds, each of which uses a different subkey derived from the original key. Block ciphers are widely used to implement efficient encryption of large amounts of data. A large plaintext is split into n fixed-size blocks of 64 or 128 whatever bits, and the encryption transformation is then applied to each block. In itself, a block cipher is designed only for the encryption of a single block of data at a time. To chain together blocks of bigger plaintext, various modes of operation, also known as block modes, are used for encryption and decryption. To securely encrypt amounts of data larger than a single block, a cipher is combined with the block mode of operation. Commonly used block modes include cipher block chaining mode, cipher feedback, output feedback, counter mode, Galois counter mode, and others. Block cipher modes of operation can be constructed in various ways. The most straightforward is electronic codebook, or ECB. It simply divides the plaintext into equal-sized blocks and encrypts each block separately from the others. A commonly used block mode is cipher block chaining mode, or CBC. Encrypting large input data with a cipher operating in CBC mode works as follows. The encryption algorithm state is initialized using the secret key and an initialization vector. The first block of plaintext is encrypted, and the next block of plaintext is XOR with the previous ciphertext block before being encrypted. This way, each ciphertext block depends on all plaintext blocks processed up to that point. Then the next portion is encrypted, and the encryption result is again XORed with the next plaintext block, and so on, until all the input data is processed. The decryption works in a very similar way. The output feedback mode, or OFB, instead first encrypts the initialization vector and then XORs the plaintext blocks directly with the ciphertext after the encryption of each block. Counter mode, or CTR, encrypts blocks separately but keeps a counter of the block's distance from the beginning of the input with each block encrypted. Different designs of block modes carry different processing speed and security properties useful in different applications. Block ciphers split plaintext into blocks of fixed size for processing, but it's very common that the input length is not divisible by required block size. Like here it's 8, and the last block is just 2 bytes long. If the last block is shorter, some block modes like CBC require for it to be padded to the required block lengths using a padding algorithm. For example, fill it with some special padding bytes. One common padding is PKCS7. The value of each added padding byte is the number of bytes that needed to be added to the last block. So in this case, there were 6 missing bytes at the end, so the last block will be padded with 6-byte value 6 times. In the Wolfram language, the partition into blocks and padding can be done in a single line operation as follows. By convention, even if the message splits into blocks evenly, it is still padded with a whole block of constant byte values. Like in this case, that would be all 8s. This way, the decryption algorithm does not have to guess if the original plaintext was padded or not. It is always padded. Some block modes, like CDR, do not require padding because they XOR portions of the plaintext and the internal cipher state at each step, regardless of the length of the final block. Initialization vector, IV, sometimes referred to as nonce, salt, or starting variable, provides the initial state to certain block modes. The IV should be unique and unpredictable for each encrypted message, but not necessarily secret. The size of the IV is usually equal to the cipher block size. For example, for IAS, it will be 128 bits. The same initialization vector should not be reused to encrypt multiple messages with the same key. Like this, two messages start the same, and the reuse of the IV causes the encryption of the same chunks of plaintext to result in the same chunks of ciphertext, which creates opportunity for attacks. The decision on which block mode to use depends on the application security requirements and the cryptographic objectives one is trying to achieve. CBC block mode can be used to achieve confidentiality, but does not provide authentication or guarantee data integrity. The CBC mode works with blocks of fixed size and so requires a padding algorithm to make the last block needed lengths. Most applications use the PKCS7 padding scheme or ANSI X923. On the other hand, the counter block mode can process arbitrary plaintext lengths without a need for padding. It is a solid choice with no significant flaws currently known. Another advantage of counter mode is easy parallelization of encryption and decryption. Similarly to CBC, it is used for confidentiality. The Galois counter block mode has all the advantages of the counter mode and additionally produces a message authentication code. Galois counter mode is an efficient way to implement authenticated encryption in symmetric ciphers. Certain block modes are not recommended for use at all. A well-known example is electronic codebook. With ECB, equal plaintext blocks produce equal ciphertext blocks. As a result, rendering the encryption insecure. If you look at this image of SPY key encrypted in ECB block mode versus encrypted in counter block mode, in the first one, you can still kinda see the SPY key. Some block modes, like cipher feedback or output feedback, can encrypt input data continuously regardless of the length of the plaintext, since they do not require padding. This is useful for applications that transmit data in streaming where it is inconvenient to add padding bytes. Many block modes, including counter and Galois counter, support random access decryption, like seeking an arbitrary time offset in a video player or playing an encrypted video stream. Effectively, these block modes make the block cipher act as a stream cipher. Stream ciphers encrypt a continuous information stream 1 bit, byte, or frame at a time with a continuously updated stream of key bits. The ciphers are used in applications where expected plaintext size is not fixed, is to be processed in real time, and may be generated without intermission for an unknown period of time in the future, such as radio transmissions, video streaming, voice or video calls over the internet. Stream cipher specifications and implementation employ many different techniques, including shift registers, nonlinear filtering functions, and modified versions of block ciphers. The following example is an illustration of a stream cipher that processes a video stream 1 frame at a time, applies an encryption transformation to each frame, and results in another video object with its context obscured. The initial key is changed with every frame as well. Imagine you need to encrypt this video of a bird frame by frame in real time. Each frame can be encrypted using an algorithm similar to one-time pad. A secret key is generated to be the same byte dimensions as the video frame, and every byte of the frame is XORed with the corresponding byte of the key. This is called a binary additive stream cipher. Generate a key with the same byte dimensions of the video frame. And define a function to encrypt a frame by XORing it with the random key. Take the image data of bytes of the frame and apply bit XOR to every byte and convert it back into the image object. As you can see, the encrypted frame bears no resemblance to a bird. To encrypt the whole video stream like this, make the key change from frame to frame by adding the frame index to it. Here is the encrypted video. You can see that something is moving, but you cannot quite grasp what it was. Stream ciphers draw a loose inspiration from the one-time pad. However, they do not reach the same level of security. The key for stream encryption will be as long as the raw stream, but it is not perfectly random as required by one-time pad to be unbreakable. The key stream is pseudo-randomly derived from an initial short secret key that is distributed between parties.